Time magazine called him the unsung hero behind the internet. CNN called him a father of the internet. President Bill Clinton called him one of the great minds of the information age. He has been voted history's greatest scientist of African descent. He is Philip Emeagwali. He's coming to Trinidad and Tobago to launch the 2008 Kwame Ture lecture series on Sunday, June 8th at the JFK Auditorium, UWI St. Augustine, 5 p.m. The Emancipation Support Committee invites you to come and hear this inspirational mind address the theme, Crossing New Frontiers to Conquer Today's Challenges. This lecture is one you cannot afford to miss. Admission is free, so be there on Sunday, June 8th, 5 p.m. at the JFK Auditorium, UWI St. Augustine.
Thank you very much. I'm Philip Emeagwali. In the supercomputer textbooks of the 1960s through 80s, Amdahl's law cemented the theory that solving the toughest problems arising in modern calculus and in extreme scale computational physics, and solving them efficiently and in parallel across 8 or more processors is impossible. Put differently, Amdahl's law rendered sequential processing supercomputing as unchallengeable and rendered parallel processing supercomputing as a huge waste of everybody's time. The ominous shadow that was cast by Amdahl's law over the modern supercomputer was the reason that 25,000 vector processing supercomputer scientists of the late 1980s were only conducting tabletop experiments on only one processor. Back in the 1970s and 80s, I, Philip Emeagwali, had my doubts about Amdahl's law. For that reason, I was the only full-time programmer of the most massively parallel processing supercomputer ever assembled. My grand challenge was to experimentally discover the unheard of speed-up that will make the new computer super. I was the only person that was executing 65,536 experiments across as many processors. My supercomputing quest was to make the fictional factual. In 1989, I was in the news headlines because I made the fictional massively parallel processing supercomputer factual. I hypothesized the parallel processing supercomputer back in 1974 and made the technology factual by constructively reducing my ensemble of 65,536 processors to the precursor of the modern supercomputer that is also an ensemble of millions upon millions of processors. I invented the parallel processing supercomputer, and I invented the technology on the 4th of July 1989 in Los Alamos, New Mexico, United States. I began supercomputing from the realm of science fiction. I began supercomputing from the realm of an ensemble of fictionalized 2 to the power 16 processors that were married together as one cohesive internet and married by 16 times 2 to the power 16 email wires. that encircled the globe in a fictionalized 16-dimensional hyperspace. I began supercomputing, not as a supercomputer scientist per se, but as a mathematician that was more at home with fictionalized non-Euclidean geometry and topology than with a single processor. I began supercomputing as a mathematical physicist that was exposed to the factual four-dimensional space-time continuum of Albert Einstein's theory of relativity. In the decades of the 1960s through 80s, parallel processing was the subject of a titanic battle between the majority, who believed that all supercomputers should be powered by a single isolated processor, and the minority, who believed that all supercomputers should be powered by an ensemble of processors, ensemble of thousands or maybe millions of processors. In the 1970s and 80s, the parallel processing supercomputer was embroiled in controversies. Countless ridiculing statements were made about the technology of that supercomputer hopeful. That was the reason only one computational mathematician attended my public lecture on parallel processing that took place in November 1982 and took place in a lecture auditorium that was a short walk from the White House, Washington, D.C. 9 years later, my lecture on parallel processing supercomputing that I gave on July 8, 1991 in Washington, D.C. was before a standing room only audience of research computational mathematicians that were attending the largest international congress of mathematics. The top 1% of mathematicians, or 10,000 research mathematicians, read about my mathematical inventions and my contributions of new calculus and new algebra to mathematical knowledge, and read about my mathematical inventions through the cover story of the May 1990 issue of the Siam News, that is the bi-monthly news journal of record of the mathematics community that is published by the Society of Industrial and Applied Mathematics. I was not on the cover of the top mathematics publications because I was good looking. I was on the cover of the top mathematics publications because I contributed to mathematics. My new mathematics was the Philip Emeagwali formula for solving 65,536 problems at once. The Philip Emeagwali formula was mentioned by then US President Bill Clinton, who extolled my formula in his White House speech of August 26, 2000. In the 1980s, I gave research lectures on the Philip Emeagwali formula. And at the end of each research lecture that I gave on my inventions in extreme scale computational mathematics, the audience rose as one to give me a standing ovation. But they did so because I displayed the command of my materials that in turn could only come from a deep bench of ideas and knowledge. I invented how to massively parallel process and how to communicate and compute across a new internet that's de facto a new supercomputer, that's a new global network of 64 binary thousand commodity off-the-shelf processors. Back in the 1970s and 80s, I was often teased, what is this technology for which you have no name? Some named the technology a new supercomputer. I named the technology a new internet. The core essences of my computational experiments were to email questions and answers that pertained to those equations and algorithms, that pertained to those partial differential equations of modern calculus and extreme scale computational physics and partial difference equations of modern algebra, and that were generated within each of my 65,536 commodity off-the-shelf processors of my new internet that had 16 orthogonal pathways that were identical and that were equal distances apart, and to email each processor via email wires that metaphorically had a one-to-one correspondence to the 1,048,576 bidirectional edges of the cube in a 16-dimensional universe that I visualized as etched onto the surface of a sphere in a 16-dimensional universe and visualized as a new global network of processors and email wires that had no center, no edge, and email messages that had no copy, no original. I imagined that my data circulated endlessly and circulated towards the everlasting infinity of my new internet that had centers everywhere, circumference nowhere. That's like saying the earth is not the center of the universe. Those emails delivered my 65,536 computational physics codes and delivered them to 65,536 processors of my new internet that had a one-to-one correspondence to the 2 to power 16 or 64 binary thousand or 65,536 vertices of the same hypercube in hyperspace. My new internet is my river of knowledge that has 1,048,576 bidirectional tributaries that fed arithmetical data into 65,536 electronic brains. To me, Philip Emeagwali, my theory was a metaphor for the lyrics or screenplay, while my experiments represented the song or play. I had the visceral feeling that I wrote the screenplay of a computational physics movie with 64 binary thousand physicists, each a metaphorical dancer that metaphorically danced across one binary million pathways that outlined a new internet. I had the visceral feeling that I was the dance choreographer that acted in his production, which in my reality was a movie that is a petroleum reservoir simulation of extreme scale computational physics. I visualized my 65,536 computational physics codes as metaphors for as many screenplays. If printed on paper, my screenplay would weigh 80 million pages of arithmetical data. As a research massively parallel processing computational mathematician, one of my basic premises was that each partial differential equation of mathematical physics must be congruent with the law of physics it encodes and must not be contradictory to the law of physics that it arose from. To many white historians of science, a black inventor is a myth until he becomes a white inventor. I've sat for a published portrait in which the white illustrator portrayed me as a white inventor and did so to make me acceptable to his white readers. The reason my invention was rejected was that it was dismissed as a black invention and as a myth. I was mocked at, not because my theory and its companion parallel processing experiment was wrong. I was mocked at because I was a lone wolf black and African supercomputer scientist that was trying to prove that the impossible to solve is in fact possible to solve. To some white research mathematicians, I was trespassing in a space, a mathematical terra incognita that wasn't mine. In the 1970s and 80s, my mathematical discovery story that became the cover story of top mathematics publications was ridiculed, mocked, and rejected. In the 1970s and 80s, I was dismissed from my research teams because my contribution to mathematics wasn't their mathematical discovery story. In the 1970s and 80s, I was rejected and mocked because I proposed that parallel processing will work, namely that an ensemble of the slowest processors in the world could be harnessed to compute faster than the fastest supercomputer in the world. In the 1970s and 80s, my massively parallel processing supercomputing premise was that the logic of the grand challenge problem should determine how the problem should be solved, not vice versa. That is, it's only the laws of logic and physics that are sacrosanct, not the technology that in the first place must bend for the laws of logic and physics. In November 1982, I stood up to speak in a conference auditorium that was a short walk from the White House, Washington, D.C. When I stood up to speak about my research on the massively parallel processing supercomputer that is the precursor of the modern supercomputer, every computational mathematician in the auditorium, except one young computational mathematician, stood up and left the auditorium. The seminar invitations that I received in the 1980s came from American scientists who did not know in advance that I was young, black, and African. Often, I was invited and then disinvited. I was invited to deliver research seminars based on their assumption that I was a white mathematician. I was often disinvited when they discovered that I was black. Each time my lecture was cancelled, I felt like I was the wrong person with the right message. In the 1970s and 80s, I was a lone wolf supercomputer scientist because white American research supercomputer scientists that agreed on the telephone to collaborate with me withdrew their offer after they discovered that I was black and African. Often, your ideas that get rejected when you are young could lead to discoveries that wins you awards when you are old. Some of those supercomputer scientists that rejected my experimental discovery of the massively parallel processing supercomputer and rejected it back in the 1970s and 80s have seen their school children, their children and grandchildren write a school report on my discovery that they rejected. My system of coupled, nonlinear, time-dependent, and state-of-the-art partial differential equations of modern mathematics, called Philip Emeagwali's equations, were developed only for research computational mathematicians. I told mathematicians attending the 1991 International Congress of Industrial and Applied Mathematics the following: as a research mathematician and as a research physicist, I always knew the fact that the scientific discoverer discovered a truth, whereas the inventor of a partial differential equation formulated possibilities. To invent a new supercomputer is to make the impossible to compute possible to compute. To discover is to see something that was previously unseen. A scientist on a research for new knowledge is a truth seeker that is seeking new truths. A supercomputer scientist on a research for a faster supercomputer is seeking a new supercomputer and is seeking new computer. The discoverer becomes the first truth seeker. The scientific researcher is on her hero's quest for the previously unseen truth. Our never-ending quest for the fastest possible supercomputer has become our journey to the frontier of human knowledge. That never-ending quest has become a self-directed evolution in which we are both the creator and the created. That journey to the end of knowledge will force our post-human descendants of a million to know the answer to the larger question of who we are and where do we want to go. Back in June 1990, Steve Jobs was looking for a new direction. Steve Jobs was intrigued by my experimental discovery of how and why parallel processing across a new global network of 65,536 processors, or across a new internet, reduced 65,536 days or 180 years of time to solution on only one processor that is not a member of an ensemble of processors, to just 1 day of time to solution across a new internet that is a new global network of 65,536 commodity off-the-shelf processors. I visualized my new internet as encircling a globe or a hyperglobe in hyperspace. I visualized my new internet as a new global network of 64 binary thousand processors that were equal distances apart and on the surface of a hyperglobe within a 16-dimensional hyperspace. Leapfrogging upwards from the third dimension in space into the 16th dimension in hyperspace leaves the non-mathematician to wonder, where did the extra 13 dimensions come from or go to? On my motherboard, the extra 13 orthogonal dimensions were compressed into the depth, height, and width directions. That invention is my contribution to the development of the first internet that emulated the fastest supercomputer and that could be harnessed to massively parallel process across a new ensemble of 65,536 processors. My invention of the massively parallel processing supercomputer that occurred on the 4th of July 1989 changed the way we think about the new supercomputer that is the new fastest computer that should become the computer of tomorrow. My invention of the massively parallel processing supercomputer opened the door for the biggest paradigm shift in extreme scale computational physics and opened our eyes to enable us to see modern physics in a different way and to understand the modern scientific method as referring to computational science as the third science that complements theory and experiment. That invention of the massively parallel processing supercomputer garnered international headlines, and I, the storyteller, became the story and the subject of school reports titled "The Contributions of Philip Emeagwali to the Development of the Computer." The uncharted fields of knowledge is the new land to be explored and colonized. That new land is explored the way Bongo Park explored the River Niger of West Africa. The exploration of Bongo Park opened the door for Great Britain to colonize my country of birth, Nigeria. I am the Bongo Park of the supercomputer world that was searching for the fastest computation ever. I was searching for the new supercomputer that computes in parallel instead of in sequence. In the 21st century, Africa must cross new frontiers of technological knowledge to conquer today's challenges and alleviate poverty. On the 4th of July, 1989, in Los Alamos, New Mexico, United States, I experimentally discovered the massively parallel processing supercomputer. Since my experimental confirmation that the massively parallel processing supercomputer can be used to make the impossible to solve possible to solve, I am often asked to explain how parallel processing benefits you. That's like asking, what will the world be like without parallel processing? A world without parallel processing is a world in which 99 of the 100 processors inside your computer is turned off and you are computing at 1% of your computer capacity and perhaps achieving only 1% productivity level. A new supercomputer without parallel processing is reduced to the stature of an ordinary computer. A new supercomputer that is not parallel processing is like Lagos, Nigeria, with only one street light on. The fastest supercomputer costs the budget of a small nation, and it is purchased because the fastest supercomputer gives meaning to life, and because the fastest supercomputer makes the world a better place, and because the fastest supercomputer makes humanity more knowledgeable, and because the fastest supercomputer of today will become the computer of tomorrow. The scalar processing supercomputer helped the first man that traveled to the moon to return safely from the moon. The vector processing supercomputer helped man fly faster and helped the first woman that traveled into outer space to return safely from outer space. The parallel processing supercomputer will help the first humans that will travel to the planet Mars to return safely from the planet Mars. And faster supercomputers is where science fiction will become non-fiction. The fastest supercomputer is where humanity's future takes shape. Parallel processing has taken the computer into a new era. An invention differs from an engineering project. Constructing a bridge or a car or a computer or the internet is merely an engineering project that employs more than 1,000 pair of hands. But faster computers and the fastest supercomputers could not be manufactured without the invention of the technological knowledge of faster computers. I'm not the technician that unpacked the crates of the new supercomputer. I'm not the technician that installed the internal computational components of the new supercomputer. Nor am I the technician that installed the internal networking components of the new supercomputer. And I'm not the technician that hooked those components into the cooling and power infrastructures for the new supercomputer. However, I'm called the father of the new supercomputer because I experimentally discovered how and why the technology of massively parallel processing across a new internet makes the new supercomputer fastest. Parallel processing was ridiculed, mocked, and rejected by Gene Amdahl and Seymour Cray, the two pioneers of the old sequential processing supercomputer and the old vector processing supercomputer, respectively. I was ridiculed, mocked, and disparaged as the bushfowl that crowed in the language of another village. Parallel processing was only accepted after decades of protracted and strenuous conflicts against the likes of Gene Amdahl, the supercomputer boss at IBM Corporation, and Seymour Cray, who designed 7 in 10 vector processing supercomputers sold in the 1980s. At 8:15 in the morning of Tuesday, the 4th of July, 1989, the U.S. Independence Day, in Los Alamos, New Mexico, United States, I made the first experimental measurement of the world's fastest computation ever recorded across an ensemble of processors that is a new internet. That experimental discovery represents a new way of looking at the computer. To be the first is a greater achievement than to be number one or to be the fastest. There is only one first, but there will be many fastest. I was the first to discover that parallel processing across an ensemble of the slowest processors is faster than sequentially processing only on the fastest processor or only on the fastest supercomputer. It was my most pleasurable experience to be the first person ever to stand at the farthest frontier of human knowledge and invent the massively parallel processing supercomputer that is the precursor to the modern computer. On the night of the 4th of July, 1989, I had a powerful, unsettling dream. I woke up with the visceral feeling that I had permanently entered into the history books and into school reports. In 1989, I won the top award in the field of supercomputing, and it made the news headlines that a lone wolf African supercomputer genius in the United States has brought that figment of the imagination called parallel processing and brought the supercomputer technology from dream to reality. Today, the parallel processing supercomputer is in the history book and is the reason the 12-year-old is writing her school report on the life of Philip Emeagwali and his contributions to the development of the computer. I invented how to solve the grand challenge problem of supercomputing that had cast its ominous shadow over the first 43 years of the invention of the programmable supercomputer that was invented back in 1946. That invention represents a new paradigm in the history of the computer. The invention was the tipping point that led to the complete acceptance of the massively parallel processing supercomputer. That invention of the technology of massively parallel processing was immediately embodied into all modern supercomputers and is now universally used within most modern computers. That invention was the new knowledge that convinced the naysayers to change the way they looked at the modern supercomputer. Looking back, since ancient times, computing aids have improved from the dustboard to the blackboard to the motherboard and now across motherboards or across a new internet. When you are inventing something, that thing is yours. When you've invented that thing, you give that thing to posterity, and that thing is no longer yours. I believe that for thousands of years, the massively parallel processing supercomputer will remain at the essential core of the science of computing. I believe that the supercomputer will remain an extension of humanity and that massively parallel processing around the planetary-sized internet will be passed from civilization to civilization. I believe that massively parallel supercomputing will be an intrinsic part of man-made brains of our post-human descendants of year million. My moment of experimental discovery was 8:15 in the morning of the 4th of July 1989. At 8:15 in the morning in Los Alamos, New Mexico, United States, I witnessed the birth cry of a new computer that is a new supercomputer, that is a new internet, that is outlined as a new global network of 65,536 processors. I saw something no human had ever seen before. I saw an ensemble of the slowest processors in the world outperform the fastest supercomputer in the world. I got goosebumps and my hair stood on end while I watched my invention unfold. Seeing for the first time ever the slowest processors compute together to compute faster than the fastest supercomputer was the most amazing experience in my life. I was witnessing the birth of a new era in the history of the computer. I was witnessing a paradigm shift in the supercomputer world. I was witnessing a change of tectonic proportions that forever affected the way we think about the computer. I was gazing across the centuries. That 4th of July 1989 marked the moment we changed the way we look at the supercomputer. That 4th of July 1989 marked the moment when, for the first time ever, an ensemble of the slowest processors computed together and computed as one seamless, cohesive unit, and computed faster than the fastest supercomputer. For me, Philip Emeagwali, that 4th of July 1989 was a day of fire, the day the massively parallel processing supercomputer became the fire we can't put out. After my discovery on that day, trying to stop the acceptance of the massively parallel processing supercomputer became like trying to stop midnight. My experimental discovery of the massively parallel processing supercomputer that occurred on the 4th of July 1989, that occurred across a new internet, that is a new global network of 64 binary thousand processors, opened the door to the state-of-the-art new supercomputers that now compute 10 binary million times faster. That new supercomputer, in turn, creates a new computer science. Before my discovery, or in the 1980s or earlier, the 1,000 fastest supercomputers in the world used only one processor. After my discovery, or after the 4th of July 1989, the 1,000 fastest supercomputers in the world parallel processed and used thousands or millions of commodity off-the-shelf processors. The paradigm shift was from computing and communicating in the singular to doing both in the plural senses. On the 4th of July 1989, I witnessed the unveiling to the human race of a new understanding of the words computer and supercomputer. In the old dictionary, the computer was powered by only one processor that was not a member of an ensemble of processors. In my new dictionary, my new computer was powered by my new ensemble of 65,536 commodity off-the-shelf processors that cohesively computed as one seamless new supercomputer. The computer is the greatest invention of the 20th century. In 1989, I was in the news for inventing how to harness the massively parallel processing supercomputer and how to use the technology to reduce the time to solution for solving extreme scaled system of equations of algebra, and how to reduce that time to solution from 180 years or 65,536 days to only 1 day of time to solution. I was in the news because reducing that time to solution increases the odds of discovering and recovering otherwise elusive crude oil and natural gas. The June 27, 1990 issue of the Chronicle of Higher Education wrote that I, quote, took on an enormously difficult problem, solved it alone, has won computation's top prize, captured in the past only by seasoned research teams, unquote. That Chronicle of Higher Education article continued that, quote, if his program can squeeze out a few more percentage points, it will help decrease U.S. reliance on foreign oil, unquote. A discovery is like a stone thrown into the pool of knowledge. The discovery generates wider ripples each time we throw it into the pool of knowledge or apply it. The discovery in science opens up doors in technology and makes the world a better place and humanity more knowledgeable. We cannot see, hear, or feel the subterranean motions of the crude oil and natural gas that are flowing 1 mile deep underneath our feet. The supercomputer simulation of the subterranean motions of the crude oil and natural gas that are flowing 1 mile deep enables the petroleum geologist to see with his digital eyes the flow patterns of the crude oil and natural gas that are invincible to our naked eyes. The parallel processing supercomputer can be programmed to solve the trillions upon trillions of equations of algebra that arises from the extreme scale petroleum reservoir simulator is the new age divining rod that must be used to discover and recover otherwise elusive crude oil and natural gas. The parallel processing computational physicists can intellectually see within a massively parallel processing supercomputer and see crude oil and natural gas that we cannot see with our biological eyes. The parallel processing computational physicist that mathematically sees deep inside the Niger Delta oil fields of the southeastern region of Nigeria enables us to discover and recover otherwise elusive crude oil and natural gas. Crude oil and natural gas are at the core essence of Nigeria's sovereignty and identity. In 1989, it made the news headlines that I experimentally discovered how we can use our parallel processing supercomputer eyes or use a new internet that is a new global network of processors as our instrument of physics, as well as use the technology as our tool for crude oil and natural gas exploration. Conversely, if the petroleum industry didn't accept my invention and didn't harness my ensemble of 65,536 or more commodity off-the-shelf processors and didn't use them in their petroleum reservoir simulations within a multidisciplinary environment, then less crude oil and natural gas will be discovered and recovered. My experimental discovery of massively parallel processing changed the way the petroleum industry discover and recover otherwise elusive crude oil and natural gas. My experimental discovery of how and why parallel processing makes the modern supercomputer fastest changed the way we think about how to build the fastest computer. It made the news headlines in 1989 when I experimentally discovered that we could execute extreme scale computational physics codes and execute them across an ensemble of 65,536 commodity off-the-shelf processors that were identical and that were equal distances apart, and that I visualized as a new internet that encircled the globe in 16-dimensional hyperspace. The massively parallel processing supercomputer that I experimentally discovered on the 4th of July 1989 cannot be undiscovered. Therefore, a supercomputer scientist that is beginning his quest for the massively parallel processing supercomputer and beginning that technological quest today is like the person that shows up to a party after half the guests have left and the other half is getting ready to leave. That experimental discovery made the news headlines in 1989 because it was the first successful and noteworthy calculation to be executed across an ensemble of 65,536 processors and executed in a manner that demonstrated that the technology of the massively parallel processing is not a huge waste of time. My experimental discovery is the reason 1 in 10 supercomputers are purchased by the petroleum industry. The necessity to execute extreme scaled problems arising in computational physics is one of the technological grand challenges that stimulated the development of the massively parallel processing supercomputer. Parallel processing is the paradigm shift of tectonic proportions in the history of computing that changed the way crude oil and natural gas are discovered and recovered. The most important contribution of the extreme scale computational physicist, that is parallel processing across millions upon millions of commodity processors, is to attain a surer and deeper understanding of how the universe works and how to harness that new knowledge to make planet Earth a better place for human beings and for all beings. A world without the massively parallel processing supercomputer is a world in which fewer discoveries are made, is a world in which innovation is slowed down, is a world in which human progress is slowed down, and is a world in which the computer of tomorrow cannot be invented today, thus making it impossible for us to create the future. The bird sings the same song as its ma and pa. Human progress occurs when we sing a better song than our ma and pa. For me, Philip Emeagwali, my quest for the fastest computation across a new internet that is powered by 2 to the power 16 commodity off-the-shelf processors was de facto the chant of a lone wolf massively parallel processing programmer that was hearing voices from the 16th dimensional hyperspace. In the 1970s and 80s, I wrote voluminously in my private supercomputer laboratory notebooks. And I wrote with the hope that my writings will endure and survive the ravages of the millennia and hopefully become my tangible connection to our posthuman descendants of year million. I'm Philip Emeagwali at emeagwali.com. Thank you. Thank you. Thank you very much.
Insightful and brilliant lecture. Insightful and brilliant lecture.